So as I said, let's start at 10, let's say 3. So let's wait 2 more minutes. It's always a good practice to wait a little bit for those who are searching for links. Okay, 1 more minute for lunch, to launch our webinar, 50 seconds. Okay, I see new people joining, that's really great. 30 seconds to start, so we are counting down like during a space shuttle launch. Okay, 4, 3, 2, 1, go. Okay, I think we can start. So good morning, everyone. It's a pleasure to have you all here. My name is Konrad Kamieniecki. I work for Quicker Sim company. And today we will be talking about how to dimension green hydrogen installation to get the best profit at the end from that installation. The webinar, I think, will take between 30 minutes or 45 minutes, depending how many questions there will be from you and how deep we will go into the details of the webinar. And if you would like to ask any question, please write them on chat. I'll try to answer them if I knew the answer and if we have a time. But if we don't find the time, or I will not know the answer at the moment, all the questions will be recorded so I can answer them later. Okay, so let's move on. First, let me introduce who are we. So far, we don't know which one. As I said, I represent Quicker Sim company. Quicker Sim company is an engineering company based in Poland, in Warsaw. Today, we have about 20 people aboard. Mostly, we are doing engineering simulation. As I said, we have about 15 years of experience. Actually, we are commercially on the market for about 7 years, but the 8 years of previous experience was our PhDs at Warsaw University of Technology. So as you know, we are established by postdocs. And we are doing numerical analysis mostly, like computational fluid dynamics. Computational fluid dynamics is pretty broad topic. Here we include like fluid flow or thermal analysis. We also do some code development. So if we have a customer who has a very specific needs, we can write code adjusted to its needs. And we work for industries like energy, automotive, batteries. And lately we started working with hydrogen, and today's webinar will be about that hydrogen. To give you an idea what we are doing in engineering area, those are various numerical simulation. For example, one of our project was to design energy storage in form of heat using solar power. So we had some mirrors radiating the energy. Other projects were like fluid flows through cyclones, for example, or we also dealt with fuel switch topics. For example, if you had a firm case for methane, we could test what is going to happen if we supply hydrogen instead of methane, how the temperature will rise, what will be thermal stress in that fuel case. So those are topics what we can do. Also ventilation stuff, like one of my research topic was what is going to happen if we will have a leakage from hydrogen tank. Here, for example, you can see in this picture a temperature distribution in big waste boiler. So we can, based on that, assess, for example, if some sulfurs will generate or not. Our main product is a battery Telmar software. We write the software ourselves, and we provide that for customers from automotive industry. And also what we do in terms of software development is, for example, a software for photovoltaic farm design. We have a commercial customer using that. That is a Corab. And we also write software for oil and gas industry for Norway customers, how to most efficiently extract oil from the bottom of the sea. And here are some selected customers. Like I said, we work for Norwegian companies, also for Netherlands companies, United Kingdom companies, and of course, as we are based in Poland, we have customers from Poland as well. Okay, so this is the short introduction. Who are we? So now you can better understand what we are doing. And the agenda for today is I will introduce you for the hydrogen topic. So why there is so much discussion about that nowadays, and then we go to the main topic. So how to dimension hydrogen installation to get the best profit based on that. And then we do some summary, and I will tell what we can do more about that. So, introduction, motivation, why we are dealing with this topic. Actually, in the world, we have increase in energy demand, and we know that the fossil fuels are finite, so we need to search for alternative energy sources. We have also an environmental degradation. This means that we need to search for fuels which are more environmental friendly. And we have also difficult political situation. And now we have a war in Ukraine. We try to be more energy independent, so we search for solutions for that. Potential answer for that needs is hydrogen. Probably we all know why hydrogen is the good answer. One of the advantages is that we have vapor as a product of hydrogen combustion. So this is pretty important as this is environmentally neutral. And we can use hydrogen as energy store. It has some challenges, but we can use it. Hydrogen can be used as raw materials for many processes, can be used as fuel, for example, in waste boilers, and also can be used as energy carrier. And also we can apply hydrogen in industries, in many industries area. And also we can use it in transportation, especially in heavy duty transportation, like in trucks, in ferries, and in trains. So there are a lot of advantages with hydrogen. Maybe before we proceed to the main topic, let's talk a little more about some interesting facts about hydrogen. Actually, hydrogen is pretty rare element in gas state. It is more or less half parts per million. So it is pretty difficult to get hydrogen in gas state for industrial application, for example. But this is pretty strange because it is the most abundant element in the universe. Actually, as you can read here, 9 of 10 atoms in the universe are hydrogen. The hydrogen was produced during Big Bang at the beginning of our universe 14 billion years ago. And then it was transformed into heavier elements in centers of stars, but still hydrogen is the most abundant element in the universe. And here on Earth, we must find efficient way to produce hydrogen because we cannot just grab it from the universe. And interesting fact for me was also that 10% of human body weight is thanks to hydrogen. And also we have 3 isotopes of hydrogen that may be interesting. We have a hydrogen itself, which has 1 proton, 1 electron. We have deuterium, which has 1 proton, 1 electron, and 1 neutron. And we have also tritium, which has 2 neutrons, 1 proton, and 1 electron. So those are the interesting facts about hydrogen. And of course, because hydrogen is pretty new topic, maybe not that very new because the hydrogen is produced for over 100 years, but now the scale is growing, so we have some challenges with that, and hydrogen must be competitive with fuel, with fossil fuels. So we have some other challenges associated with that. So what are the challenges? The cost. As I said, it is not very competitive with fossil fuels right now. I'm not sure if I'm not mistaken. I think like 2 weeks ago, I read some news that in Berlin hydrogen gas station, the price is 12 euro per kilogram or 16 euro. I don't remember exactly, but this is not very competitive compared to fossil fuels right now. We have also some issues with production and storage, and actually today we will focus on those 3 things as they are very connected. So if we have a cheap production, the end price of hydrogen will be more competitive with hydrogen, and we try to understand how to produce hydrogen efficiently and store it efficiently, so the final cost can be as low as possible. Okay, so let's move on. Let's start with dimensioning hydrogen hub. So what is the problem? The problem is how to dimension the hydrogen hub or plant so the return on investment from such hub will be as high as possible. So how to make it efficiently? Of course, to do it efficiently, we need to take into account actual weather condition, and also we need to take into account hydrogen demand profile. So actually, actual weather condition is energy input to our model, energy input profile, and hydrogen demand is the energy output profile, and we need to connect those pieces together most efficiently. The question can be stated in other words, like how big should be renewables to make the best use of actual weather for a given location. So the question is if I should have a lot of wind turbines, or maybe it is better to have photovoltaic panels, or maybe the combination of those 2 will be best. How big should be the battery in the system, for example? Sometimes we have lack of energy from sun or from wind, so we need to store some energy to provide our electrolyzers pretty stable condition. And we also need to think how to control the whole installation. Looking into weather forecast, we can think if we should better charge battery or charge the hydrogen tank, or maybe discharge the battery. Actually, there are a lot of questions which can be asked during controlling this installation. And to explain how we do dimensioning the hydrogen installation, we will use some example. So let's imagine that we want to produce 1,000 kilograms of hydrogen daily. This means that we want to make little over 40 kilograms of hydrogen hourly. Our plant will be located in Europe nearby the Baltic Sea. So here you can see the red dot is our plant. And we assume that we are going to use wind turbines and photovoltaic panels. We also have a limited connection with the grid. The limit is 1 megawatt, so we cannot send bigger power than 1 megawatt to the grid or buy bigger power than 1 megawatt. And the hydrogen demand is not constant. It varies in time. So as you can see here, we have 1 day from 0 to 24 hours, and the biggest demand on hydrogen is at 12 o'clock, and near zero demand is at night. So that can be like for a hydrogen tank station, yes. So during the day we have a lot of cars buying hydrogen, at night we have no cars. And the first approach, what we are going to do, it will be, to be honest, pretty naive approach, but it will be our reference point for later consideration. It will be averaging the installation based on annual average data. So what does it mean? Let's start with dimensioning the electrolyzer first. So because we know how much hydrogen we want to produce, based on that we can adjust the size of our electrolyzer. And more or less, based on literature data or talking with some electrolyzer providers, I know that the energy needed to produce 1 kilogram of hydrogen is more or less 50 kilowatts hour. So if I want to produce little over 40 kilograms of hydrogen hourly, the energy needed for that is little more 2 megawatts hour. So the power of my electrolyzer will be 2.2 megawatts. So that should enable me assumed production of hydrogen. Okay, so we know how big should be electrolyzer in our installation. And now we try to adjust the renewable sources for that. For the location I selected, the average power generated by wind turbine is about 20% of peak power at the location, and the average power generated by PVs is about 10%. So I can set up an easy equation that 20% times peak power of wind turbine plus 10% times peak power of PVs must be greater than electrolyzer needs. And this equation has a lot of solutions. And for this example, I pick one possible solution, which is that wind turbine will be 10 megawatts, photovoltaic panel will be 2 megawatts. And later on, we will see how changing these numbers will affect the whole installation. Okay, so we have renewables adjusted for our simulation. And now we can also adjust the tank. I know that I want to produce 1,000 kilograms daily, so my tank will be little oversized. So I make sure that my tank is never empty, and this is pretty important assumption in this installation. And also I assume the battery is going to power the electrolyzer for 3 hours. So the capacity of the battery is 6.6 megawatt hours. So this is our starting point. And let's try to conclude a little bit our installation. We have wind turbine, PV panels, electrolyzer, battery storage. I know what are the unit prices for those devices. Actually, they can be different, but during this spring, we visited several hydrogen events in Europe, and we discussed with the device producers, and those are more or less average prices for kilowatts or kilowatts hour or kilogram for the units. So based on that, I can calculate the capex of the installation, which is 21 million euros for this particular installation. Now I can predict how much I can earn on this installation. So I want to sell 1,000 kilograms daily times 365 kilograms. So this is how much hydrogen I will produce. I'm also optimist, so I assume that my renewables provide power for my electrolyzer all the time, so I do not have to buy any power from grid, so my opex at this time is 0. So I can easily calculate how much I will earn and what will be my return on investment. So if I assume price of hydrogen 10 euro, return on investment will be 17% more or less. Actually, As I told you in the beginning, the reference case is pretty naive because we all know that the opex will be non-zero because we have some maintenance costs of the let's say wind turbines, electrolyzer, etc. But for now, this cost is not very clear. So I assume that this is zero, and I have very rough estimation what we can get from this installation. Actually, later on, I will consequently assume that the opex, which I mean maintenance of the devices, will be zero. What will be different later is that I will assume that we have to buy some power from grid because our renewable will be always very efficient. So this is our reference point. Of course, if you will be interested in something more sophisticated later on for your installation, for example, we can calculate these reference points as accurate as you need it. Okay, let's move on. So we know how the installation will work if we do some easy paper and pencil calculation based on average annual data. So let's move on. Let's try to simulate this installation using our simulation script, our approach. So we can build a model of the installation. So we have renewables, we have grid also connected to the installation, we have the battery, we have the electrolyzer, we have storage of hydrogen, and yes, we have storage hydrogen. Actually, here you see one more element, hydrogen station, but this is not included in the capex. So we can say that our installation ends on hydrogen storage. And let's add also a controller to this installation. The controller is pretty simple right now, but I think it may be useful. The controller monitors the state of battery. So here we have battery, and battery can be in low state, so it is almost discharged, in medium state, and in high state. This means that battery is charged. And we have also tank, which can be also discharged in medium state and in high state. And for example, if we have low battery and we have low hydrogen tank, this is the scenario where we can buy power from grid as we want to continue producing the hydrogen. If we have, for example, high battery and high tank, this is the case where we have too much energy in the system and we can start selling energy from renewables to the grid. And we have some situation between, but we will not go into details, that it is not very important at this stage to get an idea of what we are doing. Okay. And of course, if you want to get more accurate results from our installation, we need to take into account realistic weather data. So I downloaded wind data for the location and global horizontal irradiance for the location. And now what we'll be doing. Our model will take into account the actual weather condition. So this is energy supply profile for our installation. I will take into account demand on hydrogen, which is not constant in time. It has like a sinusoid character. I will take into account controller of the installation. I will take into account state of the tank, state of the battery, purchase of the energy from grid if this is necessary. Sorry for typo here. And I can also take into account sale of the energy to the grid, so it will add to our revenue. And I will also take into account 1 megawatt limit connection to the grid. Okay, and let's see what happens if we simulate that installation for 1 year. As a result of the simulation, we get several charts. Actually, we can make as many charts as needed. And what are you interested in? But for this demo case, I have a chart presenting generated power. So remember that PV was 2 megawatts, wind turbine was 10 megawatts. And we can read what is the total power, which is sum of those two. We see that we never exceed the 10 megawatts as we have very variable conditions. Like sometimes we have sun, sometimes we have wind. So those add those two add to this green line, which is behind those two. Okay, so we know what we have energy in the system at every minute or every hour, depending what is the time step in the simulation. Then based on that, we can read how much energy we purchased from the grid. So this is the blue line. How much energy we sold to grid. This is the orange line. And how much energy we lost. This is the red line. What means lost power? Lost power is, as remember, we have a limitation with the grid, 1 megawatt. So if we sometimes have overproduction of the energy, we cannot sell everything what we produce. We can sell only 1 hour to the grid. So the rest of the energy is lost. So this is it. And actually, based on this chart, we can make a nice conclusion that sometimes we have to buy a lot of energy, sometimes a lot of energy. So something's wrong with the dimensioning of the installation. We must search for other solutions. And also we can search for battery state, see when the battery is charged or discharged. And we can also take a look on tank state. We see what is the state of the tank. We never reach the full capacity of the tank, 1000 kilograms. And the orange line here is a demand on hydrogen. So when the blue line goes below the orange line, this means that we have demand on hydrogen, but we don't have hydrogen in tank, which is not very good for us. Later on, we will take a closer look to this chart. And let's see, the return on investment calculated using the model is only 12%. So it is much lower than we assumed using a paper and pencil approach. This is not a very big surprise as the assumption for the paper and pencil approach were pretty naive, but now we have much more realistic view in our installation. What could be difficult for investor? We assumed that the income will be 3.6 million euro based on paper and pencil approach, but the realistic income is only 2.3. So we have over 1.3 million euro difference, and it can be very painful for the investor. Okay, let's move on. Let's take a closer look for the chart about the hydrogen tank. Here on the right-hand side, you can see you have a scale for tank state, and the red line is a tank state. So you can see the tank state after, I don't know, 15 hours of operation was like near 100 kilograms. But then we try to sell some hydrogen. The hydrogen demand on this chart is blue line. So this is sinusoidal character of the demand. And the orange line is how much hydrogen we actually sold. This is the orange line, so you can see when the tank is empty, I cannot sell what is the demand, so I have lower sale of hydrogen than the demand, and the pink line is the production by electrolyzer at the moment. So based on this simple analysis, we can have pretty deep insight what happens with our installation and where we can sell or where we cannot sell the hydrogen. What else we can see there? Here is enlarged picture of what we sell or what we buy in our installation, and you can see the hydrogen sale is the green line. We also sold some power to the grid, so the total sale is this dashed violet line in here. What else? What is, I think, pretty interesting, based on simulation, we can calculate how much we produced green hydrogen. Green hydrogen is based on the power from renewables, and gray hydrogen is produced based on power from grid. So we can see the proportion, it is like 30% more or less of gray to 60% of green hydrogen. Okay. And as a conclusion for that is that the estimated ROI by the model is much lower than ROI estimated by paper and pencil approach. And this is because we took much more realistic assumption. Our solution is based on actual weather condition, on actual hydrogen demand, and also on the limitation with the grid and the purchase and sale of the energy to the grid. So we have much more realistic estimation of our installation. Okay, let's move on. And now the question is if we can find better configuration for that. So let's try to use our simulation tool to find better configuration. Now what we are going to do, I will take, for example, wind turbine size as array of different sizes. So I will have a lot of parameters regarding the wind turbine size. I can do the same for photovoltaic panel size. So I can have array of different sizes of photovoltaic panels, and I can prepare parameters for all of the components, like size of electrolyzer, size of battery, size of hydrogen tank. And then using the parameters, I made about 20,000 simulations. And the results of those simulations is on this chart. On this axis, we have capex of this hub. On this axis, I have income based on the simulation. And here I have return on investment. So taking a look on this cloud of points, I can have a general impression what is going on. If I have bigger capex, I can see that, I don't know, I can have low income here or higher income here, depending on what I want to get finally from the model. So I can pick some dots and see what were dimensions of the installation, what were the exact ROI, what was the exact consumption of energy from grid, etc. So I can pick some points, and based on this chart, I defined my criterion for good installation. The criterion was to have high ROI as possible, but also high income in this installation, because ROI will be high when capex is low. So this is one of possibilities, but when capex is low, income can be also low. So this is the point here. But I want to find some balance between income and capex and ROI. And what is the solution based on the simulation? The solution is, like you can see, I have new farm which has 8 megawatts wind turbine, 6.5 megawatts photovoltaic panels, big electrolyzer, smaller battery, bigger storage, and return on investment from that is 13.8%. It is 1.9% more than we had from the point 2 where we simulated the paper and pencil dimension installation. And yeah, so this is what we get. And you can also see operation of tank. We have only few points where we have not enough hydrogen to sell it. And now we can raise a question if it is worth to make such analysis to gain 1.9 percentage point. I mean, if it is big or if it is a small difference. Revenue for those two cases looks like this. We have 3.1 million euro annually compared to 2.3 million euro annually. The difference is over 800,000 euros. So I think those money is, I think, worth of making such analysis. So getting every year more 800 euro, I think is a pretty big deal. Okay, and this is it. We can also have a look on our save purchase charts. We can see what was the total sale. We can see what was the total purchase of the power from grid, total sale, how much power we lost. So we still lose some power, so probably maybe we can find a better configuration. We can also take a look at how much we produce green hydrogen versus gray hydrogen, and here the proportion between those two is much better. We have like 1/6 is the gray hydrogen compared to the total production. I think this chart is pretty important when we want to certify our installation. So based on simulation, we know what we can expect from our configuration. And yeah, so this is the main case. So I hope that I show you that using some simulation we can get more accurate results. We can get more realistic estimation, economical estimation of our installation, and we can find better solution. And the better solution gives us over 800 euros yearly in income. So I think it's a pretty big deal. And this is one of the possibility how we can use the installation. Of course, we can define other optimization objectives just to give you idea what else we can do. Sometimes the objectives are more or less interesting, but just to give you idea what we can do. I will show you a few more examples. For example, we want to maximize income in our installation. So based on that cloud of points, I search for income maximization. So when we maximize income, this means that I search for different configurations. So I have little lower wind turbine, I have the same photovoltaic panel, I have smaller battery. So I have different capex for this installation, and the total, the final income is 3.3 million of euro yearly. I hope you remember the last income was 3.1. So we have little higher income, but we have different capex. So the total return on investment is a little different, and we can also see the parameters of the installation there. We can see some charts of sale and purchase in this installation. We can also see how much we produce gray and green hydrogen. We have little better a proportion between gray and green hydrogen for that particular installation. What else we can check? For example, opex minimization. In this case, opex means how much power I buy from grid. So I want to minimize the power purchased from grid. So the return on investment is smaller because capex is higher. It's 26 millions. But I have the smallest amount of energy purchased from grid for this simulation. As you can see, the blue line, which is for grid purchase, is below the orange line, which is energy sale to the grid. Yes, so this is another possible configuration or objective of our simulation. And here, the amount of the gray hydrogen is the lowest, as I almost do not buy the power from grid, so all hydrogen is almost produced from green energy. So this is another objective we can do. And another objective is return on investment maximization. At this stage, I'd say that using only return on investment as only criterion to be maximized is not very good, I think, personally, because the return on investment will be high when the capex is small. So the optimization algorithm searches for the installation where the capex is small. So this means that we have small batteries, small storage, small electrolyzer, and small renewables. So we actually we have low capex of the installation, only 11 millions of euros, but we buy a lot of energy from the grid. And this particular result can be also due to that I simulate only 1 year of operation. Probably if I would simulate like 10 years of operation of this installation, the result would be different, as cost of the both energy, purchase energy, will be too big, and maybe more optimal solution will be to have a bigger battery. So as you can see, there are a lot of parameters that we can play with, and probably the results will depend very much on if we simulate 1 year or if we simulate 10 years of the simulation. Okay, I see one question. Can you simulate the configuration without connection to the grid, so no purchase or no sale of energy? Yes, we can do that. I can delete grid from the model. That is no problem. Maybe at this stage I can tell that we can build the model as you like. Actually, the program we use for simulation is our own code, so we can do what you want. If you have different scenario, if you don't want to have a battery, I don't know, or if you don't want to have a grid, or you want to have only photovoltaic panels, or if you want to have I don't know, bigger electrolyzer or electrolyzer in different technology with different efficiency, that is no problem. We can change all those parameters in the model and do what you really need. I also be in meantime, because the model was invented in June this year, and in the meantime I had several presentation to Polish companies, and they pretty often said that there are more interesting economical factors than return on investment. So if you, I don't know, in your projects would like to calculate different economical factors and set the optimization goal based on different economical factors, that is absolutely no problem. We can put this into the code and have the simulation which is best for you. Okay, so actually here you can see the optimization was based only on return on investment, so we get pretty strange results. But I just give you as a another possibility what we can do. Actually, this case may not have to be very stupid, because I can imagine that we can not to store the hydrogen directly, but we can spend it to pipe, for example. Yes, so if we can take off hydrogen through the pipe and transport it somewhere else, maybe this case scenario is not that stupid. And as you can see here, we have a very different proportion between gray and green hydrogen. This is because we buy a lot of energy from grid. We have our small resources, so we have cheap installation, but we produce a lot of gray hydrogen. So this is how it looks like. And we are close to the end of the presentation. Some summary of the installation. As you can see, I had 6 cases calculated. First case was annual average, paper and pencil approach. Then I had simulation of that case. Then I dimensioned the installation using simulation. And then I had 3 different objectives of optimization, like maximization of income, minimization of opex, and maximization of ROI. As you can see, paper and a pencil approach gave me big return on investment. This is blue line. But when I simulated that, I got small return on investment, and after optimization, my return on investment was pretty big. As you can see, for other cases, the return on investment is smaller, except the case where I only optimized the model aimed for return on investment, but it was not very realistic case. And we can see that how our income changes for those models. So we have some income for this case, we have bigger income for this case, but smaller return on investment. So I think that those charts can be helpful while making decision what installation I would like to build. And I think this analysis is pretty good as a kind of feasibility study when you think how to invest your money, what to do. So we can calculate several thousand simulation and see what the best suits your needs. And the chart below present you the proportion between green and gray hydrogen depending on the case scenario. So you can see that the best green production was for the installation where we minimize the opex. So in our case, minimization of opex means decreasing energy purchased from the grid. And yeah, so this is what we get from this simulation. And we have I have few more slides. What next? Actually, the whole optimization was performed for one controller, but we think that we can get much better installation if we also plug to this analysis controller optimization. And this is actually what we are working on right now. And we can also simulate various weather conditions, not from 1 year, but for example, we can take weather for several years past and see how this affects the model. We can try to make some predictions. We can also make simulation for various power prices. For example, on Polish market, we are going to have a big variance in power prices even during the day, so that can be important factor to take that into account. And we can also make what-if analysis, like, for example, what will happen if the price of hydrogen will decrease, I don't know, 3 times? What will happen if price of power will increase, I don't know, 3 times? What will happen if the weather will be, I don't know, 10% worse than we assumed? For example, when you take credit in bank, bank gives you some ideas what will happen, where the percentage for the credit will increase or decrease. So we can make something similar in here. Also, okay, this is pretty important. When we produce hydrogen, usually we generate a lot of heat, so we can take also heat into account. What we can do with the heat. Actually, we can do any scenario you need. So this is the model. As I said, the code is written by ourselves, so we can adjust the code as you like. And what we offer according to this model, so we offer high-level analysis of hydrogen hubs. So actually, we do not offer the code as the product. We offer you the analysis. If you are interested in such analysis. We can make a feasibility study based on our calculation for that. Sometimes it is like you are not thinking about building very new photovoltaic farm. Sometimes it's like you already have photovoltaic farms or wind turbines, and you think about hydrogen production. So we can reverse the problem. Instead of assuming that we want to produce, I don't know, 1,000 kilogram daily, we can calculate what is the optimum hydrogen production based on your renewables resources. So we can state problem in that case. And also, if you already have an installation which produces hydrogen, we can see if there is a possible improvement of your installation, playing with the controller or playing a little bit with sizing of the installation or controlling strategy. And we are talking about hydrogen, and we design our code for hydrogen installation. But if you think only about energy storage with batteries, we can calculate that as well. We can cut out the electrolyzer from the model and see how we will store the energy. And for example, we want to save energy where the price on market of energy is high, and you want to, so we can also play with that. We are not limited only to hydrogen installation. And basically, we reach to the end. So thank you very much for your attention. If you have any questions, feel free to ask right now on chat, or if you would like, here you can find my email. So you can send me email at any time you like. Here is also my cell phone. If you like to call me, that's okay too. So so this is it. I hope that it was interesting for you to listen to that. Any feedback from you will be very welcome, and I hope that we can meet soon. So thank you very much. Now I'm observing the chat. Maybe I'll get some questions. Okay, I don't see any other question. Oh, I see someone is typing. Bye. Okay. Bye bye. Okay, I don't see more questions. So thank you very much for your attention, and I hope to meet you soon. Bye bye.